In this video, we'll continue with our discussion of Lewis dot structures with some further examples. In this example, we have a somewhat complicated molecule where there's potentially more than one central atom. In this particular case, this is acetic acid. This is the main compound in what we know of as vinegar. In this particular case, you've been given a formula that is a structural formula. In this case, there's a carbon that's attached to 3 hydrogens. That carbon is also attached to a second carbon, which is bonded to 2 oxygens, and then one of those oxygens is bonded to a hydrogen atom. In this case, you can see that the number of atoms in the formula and the total number of electrons involved. Each carbon, there are 2 carbon atoms, each having 4 valence electrons for a total of 8 from the carbon. There are 4 hydrogens, each with 1 electron for a total of 4 electrons from the hydrogen. And there are 2 oxygens, each having 6 valence electrons for a total of 12 electrons. Summing those all together, you come up with a total of 24 electrons. In this particular case, then, the skeleton structure is drawn by connecting the 3 hydrogens to one of the carbon atoms. And then there is a bond between the 2 carbon atoms. The second carbon is bonded to an oxygen that does not have a hydrogen, and then the other oxygen which does have a hydrogen. This then results in the formation of the so-called shared pairs of electrons. In this case, there are 2 electrons for each of the lines seen above, or what you see down below. And so in this case, there's a total of 2, 4, 6, 8, 10, 12, 14 electrons that we've used at this stage. In order to finish drawing our Lewis dot structure, we need to take the remaining electrons. There are 10 electrons that are left over at this stage, and we first give them to terminal atoms. In this case, the hydrogens are completely satisfied in terms of having 2 electrons which are shared, but the oxygens do not have a total of 8 electrons. And so in this case, if we give 6 additional electrons to one of the oxygens and 4 additional electrons to the other oxygen, that uses up all of our remaining electrons. At this stage, we can inspect to see how many of the atoms have octets, and so, or in the case of hydrogen, the duet. Each of the hydrogens is fine, the 2 oxygens are fine, but one of the carbons does not have 8 electrons. So, in this case then, if we go ahead and form a multiple bond, we have a choice of how to make this multiple bond. And in this case, if we use the oxygen that doesn't have the hydrogen on it and convert one of those non-bonding pairs of electrons or lone pairs into a shared pair of electrons. In this slide, we can discuss the possibility of how to form our multiple bonds. Our multiple bonds are generally going to involve atoms that are in the second or possibly third period. In this particular case, you're most likely to form a multiple bonds, double or possibly triple bonds, that are going to involve carbon, nitrogen, oxygen, or possibly sulfur. So that's why we go about making the so-called double bond between the carbon and the oxygen. So in this case, for the carbon that is bonded to the 2 oxygens, we can count up the total number of shared pairs of electrons. We see that we have 1, 2, 3, 4 lines connecting that carbon to other atoms. Each line represents a pair of electrons or 2 electrons, so 4 times 2 is 8. And so indeed that carbon is now satisfied in terms of the octet.